All right, welcome to the Explainer. Every single device you've got, from your phone to your car, it all runs on a set of invisible rules. Today, we're going to pull back the curtain on those rules. We're going to look at how metals work their magic, how we actually store electricity, and uncover some incredible power that's hiding in plain sight, literally in what we think of as empty space.
Okay, so let's kick things off with a question. Imagine you're caught in a massive thunderstorm. Lightning is cracking all around you. Where's the safest place you could be? Inside a car. Which, that sounds completely backward, right? How can a metal box, something we know conducts electricity really well, possibly keep you safe from a massive lightning bolt?
Well, the answer is basically a real-life force field. It's a phenomenon known as a Faraday cage. And no, it's not magic, it's just some really cool physics. To get how it works, we first have to dive into the secret life of conductors.
See, the whole secret here, it all comes down to a simple fact. Electric charges act in very specific, very predictable ways when they're on a conductive surface, like the metal body of your car.
And that key idea is something called electrostatic equilibrium. Now, I know that sounds super technical, but all it really means is that the electric charges on a conductor have finally settled down. They found their places, stopped moving around, and are perfectly balanced.
And once you're in this state of equilibrium, some amazing rules just kick in. Any extra charge, like, say, from that lightning strike, instantly races to the outer surface. The voltage, or potential, becomes the same everywhere on the surface. But here's the kicker, the most important part. The electric field inside the conductor drops to absolute zero. And that right there, that's your force field. A zero field on the inside means you're totally safe.
And get this, it turns out the shape of the conductor matters, like a lot. On something smooth, like a sphere, the charges spread out nice and even. But on an object with a sharp point, they literally get crammed together right at the very tip. This creates this incredibly intense point of force. This power of points is the secret to everything from lightning rods to really sensitive modern sensors. Okay, so conductors can hold charge. We've established that. But that brings up a new question, doesn't it? How do we measure how much charge they can actually hold? This leads us straight to the concept of capacitance.
Let's forget the textbook definition for a second. In simple terms, capacitance is just a number that tells you how good something is at storing charge. It's its electrical storage potential, plain and simple.
Okay, the absolute best way to picture this is with the bucket analogy. Stick with me here. So, imagine your conductor is a bucket. The electric charge, that's the water you're pouring into it. The electric potential, or voltage, that's the water level. So, where does capacitance fit in? Capacitance is the width of the bucket. A really wide, high-capacitance bucket can hold a ton of water before the level gets too high. But a skinny, low-capacitance bucket, it fills up and overflows almost immediately. Now, the unit for this is the farad. But you have to understand, one single farad is an insanely huge amount of capacitance. To give you some perspective, if you wanted to build a simple capacitor with just 1 farad of capacitance using a metal sphere, that sphere would have to be bigger than planet Earth. No joke. That's why in the real world, you're always dealing with tiny, tiny fractions of a farad, like microfarads.
So if a single piece of metal is like this tiny, narrow bucket, how in the world do we build something that can actually store a useful amount of energy? Well, we need a smarter design. We need the hero of this story. The capacitor.
The design is it's brilliant because it's so simple. All you do is you take 2 conductive plates, they're sometimes called armatures, and you place them incredibly close to each other, but you make sure they don't touch. The tiny gap between them can just be air, or you can stick a special insulating material in there. And that's it. That's a capacitor. And here's the magic. This is the whole secret. Just by putting those 2 plates so close together, you massively boost the system's ability to store charge. The positive charge building up on one plate actually pulls negative charges onto the other plate, letting you cram way more charge onto the whole thing at a much lower voltage. You've essentially turned that skinny little bucket into a huge, wide barrel.
Okay, so now if you were to crack open pretty much any electronic device, you'd find these things everywhere. They're one of the most fundamental building blocks, and engineers are constantly hooking them up in different ways to control exactly how electricity flows.
There are really two basic ways you can wire them together. So if you wire them up in parallel, side by side, it's kind of like you're just making the plates bigger. Their storage capacities just add right up. Super simple. But if you connect them in series, one after another, something really interesting happens. The total storage capacity actually goes down, but now the whole group can handle a much, much higher voltage. It's a classic engineering trade-off. Do you want more storage or more strength?
So after all this, what's the big payoff? Why do we even do this? Well, it's all about energy. Think of a charged capacitor like a tightly coiled spring, just packed with potential energy that's ready to burst out. You know that super bright, sudden flash from a camera? That's a capacitor dumping all of its stored energy in one split second.
But here it is. This is probably the most important and honestly, the most mind-bending idea of this whole explainer. So I really want you to let this sink in. Where is all that energy actually stored? The energy, it's not actually in the metal plates. It's not in the wires. The energy is stored in the electric field that fills the so-called empty space between those plates.
I mean, this one idea that energy can exist in what looks like nothing was absolutely revolutionary. It changed physics forever, and it directly paved the way for our entire understanding of light. And that, of course, leaves us with one last huge question. If a simple little component on a circuit board is storing its power in a vacuum, what other incredible forces, what other deep secrets are hiding in the empty space all around us right now?